Hello everybody, thank you all for joining me on this webinar. Full disclosure, the recording audio did not make it through to the video, so I am voicing over this recording as of now, but the topics that I'll cover will be the same. We'll be going through the 5 biggest changes to SOLIDWORKS Simulation. I'm still your host, John Nikoloff, Senior Simulation Specialist and Application Engineer at GoEngineer, and we'll be basically just going through all the things we did in the webinar. Moving forward with the agenda, we will be starting at 2017 and moving forward to 2022. If you notice, I do have 6 spots for the agenda. That is because I did want to fit in some notable mentions to the list, predominantly the 2020 change for including draft quality and high quality mesh within one study. I actually did use this for the prosthetic hand, and it was a very powerful tool. However, it didn't really stand on its own to be more important than everything else. So I did want to at least give it some time just to say, hey, this is something that's really cool, and it's something that I used in the prosthetic hand model that I have here. By the way, this model was volunteered to be used by our own GoEngineer application engineer, Jacob Bukowski. So shout out to him if he is listening. It was a really big help, and it was a really great showcase to use all of these tools on one model. But I didn't just use this model. I did use a bike chain for topology and distributed coupling. I thought it was a great example because topology will give us mass reduction. Distributed coupling can give us different weight factors depending on our remote load masses. So I figured it was a great opportunity to showcase that linkage chain that I'll be using for the rest of these studies. And then after that, we'll be going through blended curvature-based mesh, and then some more mesh diagnostics, and then a linkage rod, which astonishingly worked out really great for the prosthetic hand. And it just eliminated one of the parts that I didn't have to use, so it was great. Beginning with the Hot Spot Diagnostic for 2017, I thought this was a great tool because we are able to analyze which mesh elements and nodes that are in our study that will yield bad results. But what is a singularity? What is a hotspot, right? Hotspot is a singularity where we're basically integrating over 0. So if you guys remember your math classes, if you're going infinity over 0, it's an undefined answer, and that's pretty much what a hotspot is. We are going to be building a mesh over a line or a vertex, and there's no real way for us to separate the mesh in an area, so it's just going to be over a line or a dot, and that's pretty much what it does and how it works. This is a big issue for designers and engineers because we need to have reliable data. And we can't have that if we have hotspots everywhere. If we have artifacts from our mesh, this is going to interfere with how we interpret our results and how do we present this to our team. To see this really quickly in action, where it's found, you just right-click the results folder, and you say, yes, turn on Hot Spot Diagnostic. You give it a certain tolerance, and then you run it, and you have the program look for your hotspots. To see it in action, I actually ran this for the study that on the prosthetic finger. I was able to find some hotspots as per the picture. On the left, there are some edges where it tells you which edge is exhibiting bad meshing or bad elements. If we isolate the areas that yield bad elements and meshes, this is a great way for us to analyze what's going on within the model, where the mesh nodes and elements are. And I chose to show this area because I was going to be looking through the rest of the model, and I was kind of curious to see what's going on in particular regions of the model. So you see I'm looking here, trying to get a good view of where the elements are bad, which elements are going to yield really wonky results. And it's nice that SOLIDWORKS gives us a transparency of this. Next, if we run a diagnostic, this will actually outline the individual lines and edges that will have bad elements. Now, it'll force the study to converge the mesh to yield a hotspot, and it's just a prediction tool. This isn't actually going to be changing your results. But I really like this tool because it shows us which lines, which edges we need to analyze, to be careful for. And if we can increase the mesh in those areas and eliminate those singularities, great. If we need to add a fillet, this is a great tool to tell us where we can add those fillets so we can apply a different mesh control so we can eliminate those concentrations. Furthermore, the graph on the left just show you which edges, which vertices are exhibiting these bad elements. So it's just one other tool to show you numerically and graphically, hey, this is what's going on here. And in the next example, I actually pulled up the graph of if we were to numerically show these results. At the bottom of the legend, on the below the x-axis, is a key guide that tells us which edge is being displayed, and on the y-axis gives us the von Mises stress that was calculated through that diagnostic. So the graph on the left, I have the legend as default just to show us the highest concentration for whichever edge will exhibit that artifact, and the right shows an adjusted graph to show the lower, I guess the lesser dangerous hotspots. But in another investigation, you could change the graph one more time to show those lower edges that don't yield the biggest hotspots, but there's still something there. So it would tell us that we need to continue to investigate this. But I love that this shows us the edges that are actually exhibiting these hotspots, because it just takes out the guesswork. Moving to the topology study, here I have my bike link chain, and it's a pretty simple function. It is simply just going to reduce the mass in our part. Of course, there are a lot of criteria that allow us to augment how much material is taken out, which direction the material is removed, and if we want to include any symmetry in the removal and in the allowance of whatever mass we're allowed to keep. Furthermore, once we have a finished model of a topology study, we can kick this out as its own solid body, which is fantastic if we have a fabrication team like we do at GoEngineer. It's nice because we can just give them a solid model and then they can throw this into whatever program they prefer to and then 3D print it. This is a really nice way for us to take optimized models and give it to a certain team member or another member of our company to help it see to fruition. And furthermore, I would be very, very impressed if someone had a machinist that knew how to do these small parts, because these get very, very complicated. So here is my linkage chain for the topology study. It is starting off as a simple bike chain, most amount of mass here. And before I can actually run a topology study, there are a few criteria that we have to take care of, a couple caveats. We first have to start making a static simulation around the model. We have to understand how many, where the forces are, where our fixtures are. And in this example, I have 3 studies. I have a full load, a rest load, and then a combined load. As I go through and just kind of show you the external loads that I applied to the model and the fixtures, I later put them all into a combined force or combined load. So in the external loads area of my simulation tree, I have the places where I have forces being applied to the model and a couple of remote loads being applied to the part as well. This gives us an idea of what forces will be going through the model at the time we're going to be using this. And this also gives us an objective of, okay, how much force is too much force? How much mass is too much mass or too little mass? Is this going to exceed our von Mises stresses in whichever regions that we're most concerned with? These are questions we got to ask ourselves before we throw a model into a topology study. Now opening up my topology study, we have some fun features that we can mess with. We have the goals and constraints for our model, which I've chosen to be reduced by a maximum of 50% of the mass. and the manufacturing controls. We have the preserved region, some things that we got to keep, specified thickness, a thickness in a certain region that can only be that, that small or that large. The demolding direction, which we can select a edge, a vertex, or a face, and this will be a guide for our solver to eliminate mass in that particular direction. So if you know that your forces aren't going to be really extraneous in a certain direction, that is somewhere you could say, yeah, we don't really need mass here. This is one tool to use that. The last tool is going to be the symmetry control, which governs which direction there's mass eliminated from our model. And in this example, I have a quarter symmetry model. So 2 planes cutting up my model into 4 parts. They don't have to be symmetric, but the 4 planes will govern which direction there's mass eliminated and kept. And if you change this to a half symmetry, then of course you only have 1 plane instead of 2 planes. So it really depends on how much mass you need in certain areas, how dynamic the loads are within your study. Because if you need more directions in your model, then this is where you would say, okay, yeah, this is where we're going to need more planes to say, okay, yeah, this needs to be symmetric. We need more mass here. We need to resist the forces in these specific directions. Excuse me. In the half symmetry model, open that up really quick. I have just 1 plane on the right plane. Specified half symmetry governs how many planes are input. And to show you this, I'll show you a quick example through the compare tool on what these both look like once we have run both topology studies. As the top model loads in, the bottom shows the half symmetry model, only 1 plane of symmetry to eliminate mass by, and the top one is the quarter symmetry model. As you can see, there is a difference in where there was mass eliminated from the bike link. It shows that on the bottom one, we did not have any symmetry on the plus and minus y direction, but we did have some symmetry in the plus y direction for the top linkage. And here's a different view. We had that one region in our bottom model that was well reduced. So this is interesting. So, and this really just depends on what our scenarios are, how crazy the part is going to get once it's introduced into the real world. But this is a really great tool to say, okay, we need, or we're allowed to eliminate mass in this direction or this direction. And that's how you get these really cool, topology studies. It doesn't just reduce mass and costs, it also looks pretty interesting. And this is one way we can customize the directions in which we keep our models looking good. New to 2019 is distributed coupling. Distributed coupling is when we are using a remote load mass and applying a force or a moment or a torque onto a certain part, and we do not care about modeling that actual acting part. What we can do instead is represent that virtually as a connector, and we can apply certain weight factors to that face we're applying it to. So here you saw that I had a little ping over the rigid versus distributed. Rigid just means you're applying that force at a certain distance to that part, and it doesn't include the linear, quadratic, or cubic adjustments for the weight factor. Of course, once we start applying these to the fixture or the nodes, this will change our result because we are now adding accuracy to the type of behavior that part is going to act on our part in question. So quadratic and cubic, these do have several more variables out. You can use this for more dynamic loading, or if you have a certain direction or extrapolated equation that will work with one of these, then you can apply that to your force, or you can apply that to your model, excuse me. So where W sub I is the coupling node, R sub I is the coupling node, radial distance from the reference node, and R naught is the distance furthest from the coupling node. This is what they mean. And it's really great to gain extra accuracy and insight into what's actually going on with the distributed load. and it gives us a little bit better idea of how well we can disperse that force going through the model. This is the basic setup of what I have. I have the basic pedal kind of acting on the chain of this link at this specific location. I'll go through both a rigid connection and a linear connection just to show you guys the difference between the results, and that there is a difference between them. All right, so here is the topology model. We're going to move to the regular model because the setup is still the same. I do have my distributed loads in the remote load masses, loads and external loads in the folder up above. So I'm going to show you the result here. This is with a linear connection on my remote load masses, and we can see that we actually have results at that connection. We haven't done a stress hotspot diagnostic on it. This could be legitimate. At the same time, I'm going to change the settings live for you, go through each remote load mass, and assume that we have accurate and reliable distances to use for this. So I'm going to apply these rigid connections and say now you are a linear connection, and this will add that extra accuracy to the setup and to the specific faces. So the faces in blue, those nodes, will have everything applied to it now with a linear distributed coupling method here. And I'm going to speed up the video to go through this. At the time of recording this, I was experiencing a little bit of latency, so I'm going to skip until setting up the last one. So here is my study. I am going to run it with the new linear distributed coupling load masses. And we can see that we have a difference in our result. This is because we have now added the linearity to that remote load mass. So we're able to get a little bit better accuracy in our results. Furthermore, this is also made with a pretty coarse mesh. So if we were expecting hotspot concentrations, then this is probably the model we would get it. And luckily, having that new linear distributed load is helping us eliminate that concentrations because we're no longer rigidly held to those nodes on those. The weight factor isn't rigid anymore. There's now some dissipation from that with respect to how our setup is made. For the 2022 honorable mention, notably, was the high-end draft quality mesh within one study. Now, the really cool thing about this, and it just wasn't strong enough to be its own subsection, but I did want to at least mention it here in chronological order. The two different icons for our pyramids do, in fact, mean different things. In the tree, I have selected certain items to be draft quality while retaining high quality mesh elements for some other parts. But the parts that I chose to have a draft quality denoted in these rigid lines of our pyramids means that there are linear equations. I'm not really concerned with how well they adhere to the curvature of the model because it could be very planar or something that's not needing fidelity. But the high quality elements are polynomial equations in between our nodes. And this not only helps us get accurate results because we have a little bit more flexibility with our calculations, but it also adheres to our model a little bit easier. It gets the curvature right, and it's better representation of our model and thusly of our results of what we would expect to see once we start to build this or anything in an empirical study. Now segueing into the 2021 feature, the Enhanced Blended Curvature-based Mesh. As a standard, this became the default mesh that you would start with whenever you run a study. Over on the left, you can see that there are some extra options versus the standard mesh. But what's really cool about the Enhanced Blended Curvature-based Mesh is that they have enhanced the efficiency of it, and it works really well with really crazy geometry in our model. So on the right, I have my prosthetic finger, and you can see on the really curved areas where they're starting to reach the end of our model, you can see that the mesh is really well refined down to those areas. And on the more planar regions, it's not so well defined. And that's really just to write home on how cool standard-based meshes are, because they are still applicable. There's no necessarily incorrect mesh, wrong mesh to use. It's really what's best appropriated for your model, what works best for the geometry in your model. For example, standard-based meshes, you can see that on the longer curvature areas, it's a great uniformity, but it gets really undefined in the clumpiness of the areas that are having shorter curvatures or much tighter bends. And same thing for blended curvature-based. As we get closer to those curves, there's a little bit better uniformity, but on really dynamic places, we just don't have really great definition. And blended curvature-based mesh is just fantastic. We have a uniform mesh going through this cut strip of material that I have, 2 elements of thickness, and we have uniform elements throughout the length of this, which will also result in a nice smooth result versus having our results clumped up in certain areas and having our mesh data represent a better gradient of results versus having them in regions or non-discrete regions. Moving forward, I have the first example of a standard mesh being run, and here are the results of what that looks like. We can see the planar regions having a very good definition over those, more slightly curved areas. And this is great because this shows us that the planar regions do hold up really nicely with the standard mesh. We have a pretty uniform distribution of elements, but we can also see that when we get to the teeth of where my mouse is right there, we actually start to see it fall apart a little bit because it's just not customized or not as optimized to work down to the level of detail that really is required for properly meshing those particular parts, the teeth parts. Now, while we have the good elements everywhere else, we could still probably rely on this data, but this is not as uniform as curvature-based. Now, when we go to curvature-based, we can see the small areas in those planar areas start to change, right? The planar areas are now having less uniformity, but going down to the curves and the fillets of our model, we're getting much better definition. And that's because the curvature-based mesh starts to look at the number of elements around our circle, aspect ratio. That's when it gets first introduced to the mesher. And we can further see that the teeth on this model are really well defined. And they're becoming better defined. And the planar regions are doing okay. They're not really well uniform, or the uniformity isn't the best that we would like it, best that I would prefer it. In stark comparison to the based mesh. And now the blended curvature-based mesh, it's kind of funny how it takes the best of both worlds and just keeps going with it, because we are starting to see some better uniformity on the planar regions with the number of 8 elements around the circle and 1.4 aspect ratio. But we can see that the curves of our model are being well refined, and the planar regions are still looking really good, and the teeth are looking even better than the curvature-based mesh. Likewise, we are seeing something that kind of resembles a standard-based mesh on the more planar region of this area. So that's really cool. The blended curvature-based mesh is extremely powerful. Now, in a 2023 wish list, I would prefer to have both a standard and a curvature-based mesh running my model. Blended curvature-based mesh with a standard mesh, because then you can truly access the best of both worlds. You can get the planar regions perfectly modeled, well, as close as we can, and you can have the blended curvature-based mesh really refine certain areas that you need to have that specific definition or fidelity at. You could arguably do that with a blended curvature-based mesh, but you have to be really smart with your aspect ratios and your number of elements around your circle. So it does require some customization and a little bit more tweaking. For 2021, we have the Mesh Quality Diagnostic, kind of in tandem with the stress hotspot concentration, you can see how closely related they are to each other, but it really writes home on how important meshing is to running our study. The diagnostic is found in the quality plots. When we show it, we can create one and show it. This is one I have created already. And this shows us where I was looking at aspect ratios. It was looking at poor quality elements that relate to whatever criteria you're looking at. And for here, I wanted to see where I had really large elements that did not make sense for them to be so large. And that really makes the design less accurate because we're not understanding what's happening inside those large elements. Because if we apply a mesh control there, we could increase the number of elements and nodes in that region and get a better idea of what's going on there versus having a very coarse idea or result over that certain region. And furthermore, I really like how translucent the model becomes, so we can easily see where our elements are bad, and it just takes the guesswork out of this. For 2022, we have the new Linkage Rod connector. And this is a really awesome feature because I was using this and I am relatively new to this feature, but it is yet another virtual connector that we can use that will help us eliminate the number of elements in our model. So it cuts down on the mesh time and thusly on the run time. And it gives us another flexibility of saying, okay, we don't need this in our model, but we can virtually represent it. And it's very easy to set up. All we need is 2 pins, and you need to know the geometry of your part and the material of your part. It is very straightforward. And I actually did really need to use this for this model because when I ran it for the first time, this linkage was costing me an excess of 70,000 elements and was increasing my solve time drastically because this was a dynamic part. I was saying that there were sliding in between these faces. I had to make sure the mesh was good. And once that was done, SOLIDWORKS has to actually apply those loads to the model and then equate what's going on. So since we have a virtual connector instead, this cuts down the runtime because it can better calculate what's going on versus represent what is going on. And I'll show you the basic setup of what this looks like to get this set up. So here's the model, prosthetic finger. We have the connectors now having the linkage rod selection available. I already have mine open, so I'm going to show you how I set it up. And already you can see the blue and the purple pins that I used for my selection. So after you take out or omit the part that you don't want to keep or you want to be virtually represented, we have a couple options here. In the blue box, I have selected the first pin, and in the dark blue, that's where the linkage rod connector is being represented in our model. And you can see the start and end pin start being in blue and the end being in purple. So I selected that first face of that pin, and when you make it, there are offsets that you can apply to this. I'm going to be going into the offset right here. So I have it upwards from the center point of that pin. It's going up 2 millimeters. And if we need to go down, there is a reverse direction. I'm sure many of you designers know the reverse direction. It's a very easy thing to just say, hey, flip this between here and here. Flip it right down. So you can do diagonal connections. You can also just offset it to whatever makes sense. As long as you know how to represent this physically, that's when I would use the virtual connector. Furthermore, we do have different joint types. We can call them pivots or just rigid. I was just experimenting around and seeing what this would look like if this was a rigid connection. And when we have created our linkage rod, there will be a connecting piece between the two selected entities. In a further study, I would change this to a solid rectangular part because instead of a cylinder, then you get the the length or the height and width properties, so you can further customize what an actual linkage rod is doing inside your model. And it doesn't have to be a perfectly uniform square, seeing how this kind of looks like a thin, really thin part. If that's what you're using in your design, or you want to utilize something like this in your design, the material library does work in tandem with this calculation. So you could, in theory, test a completely new linkage rod connector, use your custom library or customize it from a library, or customize it on the fly, and then try to build a representative model of that, and then do a full robust test. Of course, those robusting testing, that's safe for the latter end of the study. But the linkage rod connector is fantastic because we can incorporate actual material data from your data sheet, from your supplier, either now or if you already thrown it into your library, you can just recall it here. So a lot of great options and further flexibility that we're allotted with for the linkage rod connector, and the further virtualization of these connectors that cost us a lot of time to run. And here's the results of my study. As I expected, I was starting to see the highest stresses at the connection points, and that makes sense. Wherever we have nodes that are not allowed to move, that's where the highest resistance is going to be, because those nodes are just not allowed to move when the rest of the model is allowed to move. So the top two fixtures are reference geometry to a plane that kind of represents the that rod that's connecting all the fingers together, and the bottom pin is a fixed geometry fixture. And I just wanted to keep these stuck here so that we could just see what the linkage rod is going to do while we enact a pushing force on the tip of that finger. And this is just helping us get a little bit closer to a empirical data result without having to actually build the model. And I'm going to open up my details and show you the mesh elements that ended up making the full model of this. Like I said before, that linkage rod connector cost me about 70,000 nodes. So being able to cut this down from 130,000 from 200,000 significantly cut down my solve time, and I was able to finish my study and show it off to you guys. And I was actually able to use this tool, and now I can see its true value, because without it, this study does take a while to run, because it's a multi-part assembly, right? But the more value is added when we can properly represent things with virtual connectors, because it saves us on solve time and modeling. And here is the full model of the prosthetic hand. To finish the webinar, here are my honorary notable mentions. Convert shell bodies to solids is a feature that I have used with a customer before, and it was great because we had a bunch of shell bodies, and instead of going to one part to the next and deleting those shells to turn them back into solids, we can just go to the top of the menu and just say, hey, convert shell bodies to solids. Very, very nice, quick tool while we're in the design process. And I've covered draft quality and high quality mesh within one study. Fantastic way to cut down runtime and focus on what we actually care about in our model. The last two that were really great tools that were added over the years, but didn't feel like they were used everywhere as much as everything else, was energy norm error. Looks at the difference between your nodal stresses and your model planar stresses, compares the two, and gives us a ballpark of how weird our results may be. Gives us an idea if we need to reset up our model or change the setup. And free body forces. I was going to use this for this model, but I ended up fixturing it, so it didn't end up making a difference. But it's a fantastic tool if we don't have any fixtures, or if we don't know where to start with our fixtures. This holds our model together, and it doesn't use the soft springs option, which doesn't add rigidity to our model. It just lets us compute it as a free inertial body, which is also another feature that was really great to mention.